new topic, okay? The new topic is what we call estimation and bootstrap, okay? And let me share my screen and then we can start. Oh, it's here. Start from here, okay. All right, so that's the, so causality, remember we walked through the entire process of doing experiment and then how to come up with hypothesis and doing all of the testing, okay? Yeah, and thank you, Liv. I saw your message. Feel free to leave early if you need to, okay? Thanks. And alrighty, so then here, the topic 18 is now we're coming back to some more fundamental questions in some sense that, well, now we know how to do hypothesis testing, right? We know how to do it in Python. We know how to set up the hypothesis, all of the simulation, and hopefully by now the p-value decision rule also makes sense to everybody as well. But the thing is, we do have other challenges ahead, okay? So one you will see soon is that, well, a lot of times we only have the sample, right, that we're trying to test about, okay? And like, I should say in this way, a lot of times we're curious about the unknown parameter of the population, right? And then we only come up with a sample due to one reason or another, we only have it. So we need to figure out a way to test it out, right? And then we already talked a little bit about this before, like every time you take a different sample, you will have a different like test statistic or like a summary statistic that you're able to return, right? So we do know that every new sample gives you something new, right? And that's why we're able to come up with the distribution, if you remember, right? The test statistic, things like that. Okay, so here you will see, maybe not today, we probably won't be able to get it, but on Thursday you will see that, well, what if you only have a sample? How are you supposed to come up with different samples out of one sample? Okay, so that's a legitimate question to ask, and then there are ways to figure that out. So before we get there, I want to talk about a couple of concepts, and then we're going to do some demo in Python, so we know in Jupyter Notebook now, so we know what they are and how to do it. And then in the end, we're able to bring everything together into what I call like the bootstrap method that, well, if you only have one sample, what else you can do to come up with a test statistic, and then how you can do the test. Okay, so that's just a preview, I guess. Here, let's talk about the first concept. I want to get it through because this will be relevant. I mean, not only just about the concept itself, but also like how to do it in Python, and then later on how you're going to use it. Okay, so this concept is called percentiles. It's pretty, I think people know about this, like one way or another. Like, for example, I think like SAT scores, it's really giving you as a percentile, right? Not really just the raw scores. It's like you compared to others, how highly you ranked among all of them and things like that. Okay, so that's what people call like a standardized score. I mean, not only standardized test, I guess, but also the standardized score itself. So percentile, okay, is defined to be, okay, if you have a numerical array, okay, you're gonna sort it in an increasing order first, okay? And then if I'm looking at the 80th percentile, it's going to be the first value on the sorted list that is at least as large as 80% of the remaining elements in the set. Okay, it sounds a little bit complicated, but let's walk it through using this example. Let's just say we have an array of 17395, okay, 5 of them, okay? And the percentile in this case of the 80, it's 7, okay? The reason is because if you follow the procedure that I'm talking about, like you have a numerical set, right? And then you have to first of all sort it, okay, increasing order. So 17395, I should have 13579, right, in that order, because that's the increasing order, okay? And then, so I have 5 values in total. The 80th percentile is the first value on the new sorted list that is at least as large as 80% of the elements in the set, okay? So 80% out of 5 points or 5 data points is, so 80, like 80 divided by 100 or 0.8, right, times 5 is 4, okay? So meaning that you need to find the value, the first value on this list that is at least as large as 4 out of the 5. Okay, if I put it into this particular example here. Okay, so if I have 13579, right, I have 5 values in total. I'm looking at the first value that is at least as large as the first 4. So it should be my 4th value. Okay, and that's what is 7. Okay, sounds a little bit confusing, I guess, but let's see if like a few more exercises is going to make sense. But you might be wondering, okay, what if I have a percentile that doesn't really correspond to an element? Like say, for example, instead of doing like 80%, sorry, like 80th percentile, what if I want to do 70th percentile? Okay, so if I want to do the 70th, what did I do? I have to do like 70 divided by 100, right? And then times 5. What is that? 0.7, 3.5, right? 3.5 does not correspond, I mean, it's not an index, right? Like per se. But then according to the rule that we're doing, it should be the first value on the sorted list, a list that is at least as large as 3.5 of the elements in the set. So in that case, it's going to be the fourth one, which is going to be a 7 again. Okay, so this is just a rule of thumb. Okay, so try to think it through, because we do have a percentile function in Python you're able to do. Okay, and so it's the percentile method, like you can, yeah, it's a function, and then you supply the p, which is the percentile between 0 and 100 that you want to return, and then the list or like the array of values that you're doing. Okay, so keep that in mind. Let's I hope just to get it across so we're able to sort it through carefully. So this is still the old list that we have. Okay, the array 17395. I have this 4 different discussion questions for you, and then we can do a demo together just to make sure that we understand everything. So here it's asking which are true. So it could be more than one. Okay, it's not multiple choice. Okay, we're just asking true or falses for the 4 statements here. And I won't repeat it here, but because I do want to put you in the breakout room. So I would just say, if you go to topic 18, is page 5. Okay. And once I put you in the breakout room, I think because there are so many different choices here, I think it's better if you go to the slides and then look at it while you talk with your breakout room members. Okay. So it's discussion question on page 5. And we're going to put everybody back into the old breakout rooms. In this case, let me do maybe like 3 to 4 minutes. Okay, talk through all of them. Think about which ones are true and which ones are false and why. Okay. All right. Good luck. Okay, welcome back. Okay, so I hope you all had a good discussions. Hopefully, a few debates and everybody agree on with each other. But of course, if there's any discussion, that would be great as well. So there, again, we know that when we're trying to figure out, so all of this are Boolean, right? We're checking if it's true. Okay, so that's why we're asking like true or false. Okay, so that's one thing to remind everybody. And then of course, here, like I said, it's not multiple choice. Multiple of them could be true. Multiple of them could be false. Okay, so we're gonna see it together. And for us, just so you know, if we go back to the definition, right, you always need to sort the data first, okay, in the increasing order, and then think about the percentile and stuff like that. Okay, so instead of like talking it through like without any base, let me just do it in Python, and then we can double check that we all agree with each other. Okay, so the first one is the 10th percentile of this S gonna be 0. True or false? Feel free to type or just speak up. Okay, I'm seeing some chats here. Okay, false. Okay, thank you. Alrighty. Yeah, so first of all, I guess one thing to say is that whatever the percentile that you're able to come up with, it has to be one of the numbers, right, in the original list in the first place. So I guess for that, at least we know that it's going to be false, right? And if I ask the follow-up question, what should be the value for it? I think it will be 1, right? Because 1 is the 20th, right? And then if we go back to the definition here, sorry, let me do it over here. Okay. Yeah, because like, so if I replace this with 10, right? The 10th percentile is the first value on the sorted list that is at least as large as 10% of the elements in the set. Okay, so 10 element is what? 10% of the elements out of 5. Well, it's 0.5, right? So we're gonna jump to the right, like the first value that appear in the list, the sorted list, that's gonna do like serve the purpose for that. So I think if we do, yeah, maybe a quick way for me to check would just be returning this, right? It's going to be 1. Okay. And the reason is because we go back to the definition. Okay. Alrighty. What about this one? This is saying that the 39th percentile is the same as the 40th percentile. Okay. I see some nodding. Okay. And great. Yeah. So this is again, because it's always the first one, right? That will do. So in our case, if I come back to this example one more time, right? 40th percentile, right? So it's as large as the 40% of the elements. So if we do that, it's what? 40 divided by 100 times 5 is 2, right? So we know that it's going to be like 3, right? Once we do the sorting. But then it will be the same as the 39th, okay? Because the 39th will be the one smaller, like if it's going to, what is that value? Well, I cannot do the math right now. What? 39, right? 39 divided by 5, whatever that value is, should be that order, that like that particular percentile that we're working with. But it's going to be slowly slightly smaller than the second value that we have. But remember, if it does not correspond to an exact element, you're going to take the next element instead, right? So it's going to be 3 again, I think, in that case. All right. What about this one? 40 and 41, the percentile. Now it starts to be at that like cutoff point, right? Like if it's 40, we know that's going to 2. It's going to be a second value, which is 3, right? But then if we jump to 41, though, unfortunately, I have to go to the next value, which is 5, right? So in this case, I agree. I think it's going to be false because for the 40th, it's still 3. But then for the 41st, it will become 5, okay? Just by the definition itself, okay? The last one is the 50th percentile is 5. I guess that's good, right? It's in the middle, right? And 50th percentile tells us it should be the middle. Thanks, Matt, in the chat. Okay, so that's true as well. And this is actually, the 50th percentile is the concept of median, okay? And we have been using that a lot to some degree, I guess. So just to remind you, the 50th percentile is the median. And then for us, in this case, because it's 5 values in total, right? So you do have a middle point, okay? But then if it's a 6 value array, then we know that, well, we have to jump to the next value, okay? Alrighty, another example here, not so much as example, just to show you like how you're able to like compute things like manually if you want, okay? So if I have an array of 43, 20, 51, 7, 28, and 3, okay, if I do that, then we know that, well, if I want to get the 55th percentile, then we have to sort the data first, right? Which gives you this new array, okay? Sorted with increasing order, right? And then we're gonna figure out where the 55th percentile could be, okay? You can do one line of code, okay, by doing the percentile like what we're talking about, right? This is the function. But then of course, like I said, if we go back to the definition, right? I'm trying to find not the third one, but the fourth one, right? If I'm looking at the index, the one that I should be looking for. So it's going to be 1, 2, 3, 4. And that's why it's 34. Okay. And this 55 divided by 100 times 6, that's exactly what we mean down here with the definition. Okay. So like I said, this is not so much like an example of using the function, the percentile function in Python per se, but this is still, I think, helpful for us to think through well. If you do have, because we had a nice example of 5 values, I mean, the first 5 odd numbers, right? So it might be easier to think about. But if you are working with any array, in this case, well, not great pattern, like not clear pattern, I would say, among them. So you have to think it through a little bit more. Okay. All right. Sorry for the delay. I think we're running out of time, so I'm going to stop share and stop
computer. And then I'm just going to pause. All right. Happy Thursday. We're going to pick up where we left off last time. Last time we talked about percentiles, and today I want to pick up from there. And really today is kind of an exciting day because we're going to introduce this bootstrapping technique. And this is a very powerful technique for understanding when we don't have access to an entire population. How do the bootstrap technique will allow us to make inference on the broader population with just a large sample from the population. And so it's a really powerful technique. And so I'm excited we're getting to that today. But first, I want to talk about estimation. And so, estimation is another form of inference, right? We don't have the entire population, so we're going to do an estimate of that based on a sample from that. And so, some questions we can ask about estimation is, how big is some parameter that we don't know in the population? And so if we had the entire population, right, if we conducted, for example, a census, if we had the whole population, well, there wouldn't be a need for estimation, because we could then just calculate the statistic we're interested in, and then we'd have it. We'd have the absolute answer. We'd calculate whatever parameter, whatever statistic we want, and we're done. But the problem with that is we usually don't have a census, right? Because that's really, really expensive. You know, we only do a census like one every 10 years because it costs so much money and time to process all that. So most of the time, we're not going to have access to the entire population. So what we're going to do, and this is a very powerful technique, we're going to take a random sample from that population. We can't get the data from everyone, but we're going to take a random sample from that. Okay, and then we'll calculate. We'll take this the statistic that we're interested in, and we're going to use that as an estimate for the entire population. All right, let's take a look at that. All right, so from here, what we're going to do here is we're going to actually take a look at this data about wages from San Francisco public employees. And so in this example, we actually have all of the data. We have all of the data, and we're doing that in this case because we really kind of want to see these techniques. And so we can actually compare to ground truth. And so here's this table here. And the thing that we'll be interested in is we'll look at salary. We'll look at salary from this, and there's a lot of other information in here. And so once we have that, we can look at this total compensation, which is salary and other benefits. And we can see in San Francisco in 2015 who was making the most money and what their jobs were. And then if we kind of scroll over a little bit here, we can just fit everything in. We can see, and this is like city employees from some of the government offices and hospitals. And you can see the chief investment officer. I assume he's doing, you know, like finance and managing retirements and things like that. He got the top total compensation. And then there's other departments from there. And by the same token, we can see who's kind of on the bottom of that list. And when we get down to this part, the data gets a little kind of fuzzy. We're going to see some really weird things like negative total compensation. And so that comes from some oddities about if you were switching from one position to another versus calendar year versus fiscal year. And so kind of down at the bottom, the data is a little less clear cut. So what we're going to do here is let me just rerun that again. Whoops. What we're going to do is we're going to basically remove any salary against some minimum. And so let's take someone, say, working part-time, at least 20 hours a week, making $10 an hour for a year. And so we'll calculate a minimum salary, and then we're just going to take that total compensation and then just remove any salaries below that. Okay. So now that we've kind of cleaned up our data pretty minimally, now we can kind of start computing statistics on that data. And so let's just take the median income of this population. And so again, I want to kind of emphasize the fact that this case, we have the entire population data here, right? And so we have this, you know, we have the census data. And so this population median, that's going to be the exact value. And we're going to use this as ground truth to see how our techniques fare, our estimate fares against ground truth. Okay, so in this case, the median salary was a little over 107,000, right? And that, again, that's ground truth, right? We can run this, right? We're not doing any experiments, we're not doing any randomization. This is a pure statistic computed from the population from there. Okay, and so now what we can do is, again, in a typical case, right, we don't have the data from everyone. And so what do? We sample. We take a large sample. And that's what we're doing here in this cell here. We're going to take a large sample. And again, think about when you do a survey, you're not going to ask the same person, you're not going to have them fill out the survey twice, right? So when we do the random sample, we're turning off replacement. Okay, and so what that means is that every sample is going to be, of these 300, will be unique. Okay, so we'll take that sample, and here just is, we're just showing just a sample of our sample. We're just showing the first 5 things from there, just to make sure that the data is kind of what we expect, right? And again, if we run this, we're going to get different results each time. Okay, so now we can compute a statistic of our sample. And again, we're just going to take the median salary, the 50th percentile from that. And we're going to see that that's going to be a little bit different from the ground truth. Ground truth was like about 100 and little over 107,500. And this was 111,000. So 107,000, 111, right? So they're kind of in the ballpark, but they're not exact. And that is expected because we're taking a sample. We're taking 300 out of the total table, and how many there was about, after we did that, I didn't get there, but we can just, if we just do SF here, we can see there's about 38,000 rows in that. Okay, so we're taking a small subset, or fairly large. 300 out of that sample is fairly large. Okay, and so now we can take a look at the population data. So again, this is the true population, which we normally wouldn't have, but we're going to use that for comparison's sake. So let's look at the distribution of the population. And so we get this particular distribution here, and now we can look at our sample data, right? And the idea here that we talked about earlier in this course is if that our sample size is large enough from the population, the distribution is going to resemble the population. The sample is going to resemble the population. And we can see, it does. It is not perfect, but it is a pretty good approximation of our population. Any questions so far? So the idea here is, so we have this population, and we're going to take a sample of that. And then the statistic that we compute on that, the statistic we compute on that will be an estimate of that sample. Okay. Again, any questions? All right. Okay. So now, once we've done that, once we've taken our sample, we've gotten our statistic. Now we can look at the variability of that estimate. And what do we mean by that? Right? When we did one sample, we took our 300 without replacement, we got one estimate. Right? But as we saw, it's a random sample. So if we'd taken a sample at some other time, it could have come out differently. And hence the estimate would have been, could have been different. Okay, so the questions we want to ask is, if we took different random samples, how different could that estimate have been, right? What is that variability of that estimate? And that variability is also going to tell us something about how accurate our estimate is. And the way you can look at it is that the estimate, the thing that we're measuring from our sample, is going to be equal to the true parameter. The true parameter, sometimes that's known, unknown, and well, for our example, we have that, it's known, but many times it's going to be unknown. But conceptually, you can think of the estimate as going to be the truth, the ground truth, the parameter we actually want, plus some error, okay? And this is kind of the thing we would like to kind of understand more about, like how much is that error? Okay, and so one way that we can do that is we're going to put what we did before, okay, in a function. Okay, so we have our generate sample mean here, and we're going to pass in the sample size from there. And so this is going to generate one sample for us and compute the statistic for us. Okay. And so again, we're sampling the population. Notice the table that we're using is the population table. So the San Francisco table. And we're going to sample our sample size, which gets passed in as parameter. And again, because we're sampling the population, we're doing it without replacement. We're doing it, so each sample is going to be unique. And then the statistic that we're interested in is the median, which is the 50th percentile. And so we're going to return that from the total compensation column, because that is the column that we're interested in computing the statistic from. So this function will generate one sample and return that one statistic. Okay. And so if we run that, we can see every time we run that, we're going to get something different from there. And then the error, kind of taking that that equation that we looked at in the slide, the estimate equals the parameter plus the error. So what is the error? The error is going to be the estimate minus the parameter. Okay, so the parameter is our ground truth, and the estimate, we're going to subtract the estimate from the parameter. And the order is important here. The order is important here because you would like to know whether the estimate is if it's negative, that means the estimate is too low. If it's positive, that means the error. If the error is negative, that means it's too low, and that your estimate is too low. And then if the error is positive, that means your estimate is too high. Okay, so the order is important for that. So if we calculate that error, we can see that's how far off we are. And so we can see the error is positive. So we know, because we have the ground truth, we know that our sample was too high, right? So if we took, the idea of looking at this is if we took the parameter and added our error to it, we would get back the estimate from there. Okay, so a positive error means that our estimate was too high. Okay, so we have some error, but how large or small or how unusual is that error? And so today, right, for this population, since we have ground truth, we can just resample. We can just resample it multiple times and see how our median varies, right? This is not the normal. This is not the normal case, right? Because remember, each sample, we're going off and doing like a survey or getting that population. That's the thing that's expensive. But since we have the full data, since we have the whole population data, which we usually don't have, but in this case, and computation is cheap, we can run our experiment, right? So remember, this was the thing that we ran up above that generated one estimated statistic for us. Let's just put that in a for loop and let's do that 1,000 times and then look at the distribution from there right now. So it's going to take a little time to run. And then if we take a look at this, we can see, right? So what I'm doing here is I'm doing the histogram of our sample. So each time we did this for 1,000 times, we took a sample of 300, generated our statistic, and now we're looking at the histogram of all of those. And you can see I've marked with the scatter plot, I've put our population median, right? So that's our ground truth. Our ground truth is the dot right here. And you can see the distribution, and this is good news, kind of follows this bell-shaped curve around our samples are kind of clustered around the ground truth. So this bodes well. This bodes well for our technique from there. Okay. Any questions? Any questions about the demo and what I did there? Any Python? If I went too fast, if there was any Python that we did. The good news is that these are all of the techniques that we've kind of known and come to love, right? So here we have the accumulator pattern where we're just accumulating results. So we initialize we initialize our name that we want to store these things to the empty array, and then we run this this loop 1,000 times, and we're accumulating the results using the NumPy append from there. And then once we've gotten that, we're just we're extracting. So we have the sample medians, the medians, right? That's an array. And so to use the histogram function, we need to turn that array into a table, and we can do that with the table constructor. And then we're saying, give us a brand new table. And then we're just telling it the column as an array, the sample median. And then once we have the table, we can do the histogram of that. And then this line down here, this is just showing the point there. And so this is just doing a scatter plot. So that's just showing us a point. And that point here is the population. So this is going to be the X value. So where it shows up on the X axis. And then this is just the Y value showing that I want to show it down here at the bottom. And I just gave it the color. And then I just said the size of the dot. So that's kind of all that's going on there. And then that semicolon here at the end is just suppresses the output from the scatter plot. If we take that off, it just prints a message to the screen. It just says it prints out this whole thing from there. So that just, the semicolon just says suppress that output and just give us the plot. Okay. All right. Any questions? Okay, I will move on. Please feel free to kind of shout out, pop a message in the chat. Let me pop up the chat window. I'll have that going. So if you have any questions, ask me, please ask me anytime. Okay, so we calculated the statistic. We ran that experiment a bunch of times, 1,000 times, to see kind of the variability. And so now kind of comes to the crux of the matter, okay? What we did to kind of get a sense of our variability was we ran that experiment 300 times. We did another sample. That's usually a very expensive operation, right? One sample, one estimate, but that was getting like a survey of like 300 from our population. So if we want many values of the estimate, we have to do many random samples, and that's expensive. So most times we can't go back and sample again from the population because each time costs, it takes time to do a survey, it takes money to do a survey. So are we stuck? Are we stuck? We're kind of in a bit of a dilemma here. How do we kind of get more estimates of our statistic without re-sampling the population? Okay, I'm going to end this video on a cliffhanger. So, because we're going to start the next topic from there. So, how do we get our way out of this dilemma? Is the question that we're gonna. All right. So hopefully I didn't leave you hanging for too long if you're watching the video. So are we stuck? So how do we get multiple samples? And to the rescue of this very powerful technique called the bootstrap. And so how does this work? So what we're going to do is we're going to simulate repeated random sampling. And so what do we mean by that? Well, so again, all we have is, so we have the population, which is too big to sample, to take a census of and get the entire population. So all we can do is sample, and we just have the time and resources to sample that once. Okay, so all we have is this original sample. And so presumably if we've done our sampling right, we have a large sample with respect to the population we're trying to measure, and it's random. Okay, so that's key. We want to make sure that our original sample is large enough and truly is random. So if it is large and random, we can make the argument, and we've made the argument in the past, and we've seen this, if our sample is large enough and random enough, it resembles the population itself. And we saw as our sample got larger, it resembled the population more close. The larger it was, the closer it resembled the population. Okay, so if our sample is large enough and random, it probably is a good representation of the population. And that's the key. That's the kind of the key crux here. And so what we can do is, since that sample, if it was large enough, probably it resembles the population, we're going to sample from our original sample. So we're going to sample at random our original sample. And that is the bootstrap process, bootstrap. And I think the picture, kind of drives this point home. Okay. So we have on our right there, the population, and that is unknown, right? This distribution here for a particular statistic is unknown, but we can do a sample. If that sample is large, it resembles the population. So what we're going to do in the bootstrap technique is we're going to assume that the sample is our population. And what did we do back the previous part of the course? That's what we did was we took repeated samples. And so we're going to resample the original. We're going to resample the first sample that we did. Okay. And each one of these resamples is going to be now it's going to generate a new estimate for us. Okay. And because the sample that we took is original enough to the population, this technique will work out well. This technique will work out. Okay. And so again, why are we doing this? It's worth reiterating this point. We wish we could get the entire population, but what's on the left-hand side, but all we got was this sample. And so we're going to treat this sample as if it were our population, and we're going to take repeated samplings from our sample. And so we're going to call them resamples. Okay. Okay. And so the key to making all of this work is that the resampling must be from the original sample. Okay. So we've taken that one sample. We're going to resample from that, and we must draw at random. Okay. So it has to be a random sample it has to be a random resample. And this is important, right? This is very important. We're going to do this with replacement. Okay. And this is different than what we did when we got the original sample. When we did the original sample, right, we did it without replacement. We're not going to ask the same, surveys twice of the same, individual. But here we're going to do it with replacement. And why we're doing this? Because when we do the resampling, we are going to resample as many times as the original sample contained. Okay, it's going to be the same size. So in the example that we looked at, when we sampled the population, we took 300 samples. Each resampling is going to be 300. So we're going to resample that population. And if we did it without replacement, if we took the same number of samples, we took 300 samples without replacement. Well, if we kept drawing them out, what did we get? We didn't do anything at all. We just got our sample back, right? So if we did it without replacement, we just get the original sample if we took all 300 samples. So the key here is that we're going to do it with replacement. We're just going to draw randomly from that. When we take a value, we'll put it back, and then we're going to draw again. Okay. And we're going to do it as many times. We're going to do it the same number of times. And that is going to allow us to compare the resamples to the original sample. Okay. And so that is kind of the groundwork. Those are the rules. Let's now take a look. And while I kind of set up the demo, any questions about that? I think the demo will help make it clear, but I'm happy to entertain any questions. Okay. Okay. All right. So we're gonna stay with our San Francisco data, and this is just loading it in before. And then here's the number of rows once we've taken once we've gotten all the non-part-time people once we've cleaned up the data. Again, just like before, what we're looking at here is the actual population, So this is the distribution of the ground truth from here. Okay, and then that's the same result that we got last time. Good. Okay, so that's our ground truth. That's our entire population. So now we're going to take our random sample, right? We did this before. And again, so we're sampling our original population down here. And so we're going to do it without replacement. Okay, without replacement. So with replacement is false. Okay, so now that's our sample. That's our sample. And we can see, I can't fit everything in there, but you can see it's pretty close. It's pretty close. And so what we're going to do is we're going to treat this now. We're going to treat this sample as our population. Okay, this is going to be our population. And now we're going to calculate statistics from this. Okay, and again, down here we just calculated. So this is the truth, the population median ground truth. And then here is the sample median, right, from this statistic from here. And you can see it's again, not a perfect reflection of our ground truth, but it's pretty close. So now what we're going to do is we're going to have it write a little helper function that just samples one median. This is not new. We did this before. And then we're going to accumulate. Okay. But the difference here is, so this is our one sample, right? Okay. So what we're doing, this is just a repeat of what we did before. And so this is getting the distribution from the truth. Okay. So this is not the bootstrapping. Right, because we're drawing from our original sample without replacement. Okay, and so this is what we looked at before. This is our population median. The red dot is ground truth, and this is the distribution from the population. Okay, so that is all kind of setting the stage. That is what we looked at last time. So now we can use the bootstrap. Okay, so what we're going to do is we're going to sample our original population. Right. So our sample here. Let me make sure I get this right. Yeah. So our sample is our sample from the original data. So this is the one that we're going to be using from now on. And so this, again, now because we have with replacement with true, this is going to generate a bootstrap sample. This is going to be a resample. We're going to sample with the same size. The replacement is true. So that's going to generate a new sample, which then we can look at. Okay. This is now one resample. This is one resample. So now we have three statistics, okay, that we're looking at. Again, all of them the median. And so here, the first one is ground truth. This was our sample median. And the bootstrap was a resampling of this data, of our sampling data, okay? And because it's random with replacement, you're gonna get a different result each time because you're gonna draw of those 300, you're taking 300 samples, but again, because it's with replacement, you're gonna get some variation around that from there, right? So, I mean, we can just run this again and we can see we get different numbers. In this case, wow, we actually got the bootstrap sample median was the exact same from there, but again, that is not always the case from there. Okay, so then what are we going to do? Same technique that we did before. So now that we're resampling the population, we have kind of the framework set up for that, and now we're going to do that. We're going to do that a certain number of times: 1,000, 5,000, 10,000. For this example, just the book is using 10,000. From there, just so I can run these demos fast, I'm just going to do 1,000. And I want to make note is, again, we're using our sample. We're using the original 300 sample that we got from the population data, right? Notice in here, in any of these statistics, you know, SF pop, right? Our original table was not harmed in the making of this, was not used at all from that. And so again, this is the same function. Computing one statistic. From there, it's going to do the resample and calculate our statistic, our median from there. And then once we have our helper function, we're just going to do that 1,000 times. And then now we can look at the distribution from there. Okay, and we can see the ground truth. Our population median is red, so that is actually ground truth. And here's the distribution of our medians, right? So that is the distribution of the 1,000 trials. And if we take our sample median from that, we can see our blue, we see that it's pretty close. It's pretty close to that, okay? So resampling, if our original sample is large enough, can give us can give us an estimate of the statistic that we're interested in, right? Again, you know, in most cases, we wouldn't know what the red dot is. And so what we're generating is we're generating with the blue dot an estimate of that statistic. And how are we doing it? We're taking an original sample and we're resampling that 1,000, 10,000 times and computing the statistic from there. Okay. Any questions? Okay. Great. Fantastic. All right. So that is the bootstrapping technique. And again, this is an important technique that kind of will come up again. And well, the very next topic, we'll talk about a use for that. But again, I just kind of want to kind of reiterate kind of at a high level what the framework is. So once you know the framework, coding it up is straightforward. And I want you to think about kind of what the framework is doing at a high level. And so kind of when you do these exercises, you can think about what's going on and not just copy and paste the code from the similar example. So, you know, it's like, oh, all right, yeah, here's a bootstrap here, you know, let me just cut and paste that cell. I want to think conceptually kind of what we're doing with this, right? We're going to take an original sample of our population. The population is too big to measure completely. So we're going to take a sample from that. Okay. And that's going to be our sample. And to generate, and so we want to basically get some estimate of some statistic on the population. In this example here, it was the median salary. Okay. We don't have the entire population. So the best we can do is an estimate of that statistic. And so we're going to do that by taking a large and random sample of the population. And then what we're going to do is once we have that sample, the bootstrap technique is going to be, we're going to resample that sample. And so with replacement. And so whatever that sample size is, if it's 300, 500, however that original sample size, we're going to do that. We're going to do that random sample and then calculate the statistic on that. Okay. And then we're gonna redo that. We're gonna redo that resampling 1,000 times or a certain number of times. And then from those resamplings, we can get the statistic an estimate of the statistic that we want. Okay. All right, let me stop the recording here.